Section 1.6 is an introduction to functions. We're going to start by defining a relation. And a relation is just a set of ordered pairs. For example, if I were to make a set consisting of the four ordered pairs 1, 5, 2, 3, 3, 4, and 3, 6, that would be a relation. Now the domain includes the set of all the x coordinates. So if we look at these ordered pairs, the different x coordinates are 1, 2, 3, and then 3 again. When we write a set down, we don't need to repeat a number because it's just a collection of objects. So it's just the 1, the 2, and the 3. Similarly, the range of a relation is the set of all the y coordinates. So the y coordinates are 5, 3, 4, and 6. When we write a set down, the order doesn't really matter, but I'm going to still put them in ascending order just so it's fairly organized. So I'll put the 3 first, then the 4, then the 5, then the 6. We usually like to think of a relation as an input-output relationship. This can be done by using a table, and we'll always make the input our x, or our independent variable, and the output is always going to be the y, or the dependent variable. And if we look at each of these ordered pairs, if x is 1, y is 5. So that's represented right here in this table. If x is 1, y is 5. And if x is 2, y is 3. So we have 2 and 3. And if x is 3, y is 4. So we have 3 and 4. And if x is 3, y is 6. So 3 and 6. Okay, now we're ready to define the word function. Now the function is extremely important in mathematics, and a function is a relation, so it's still an input-output relationship, but it's a relation that has a very special quality. So it's a relation in which each input leads to exactly one output. Okay, so that's the key for a function, that each input leads to exactly one output. Now let's look at the relation shown in this table and see if we can decide if this is a function. The question is, in this table, does each input lead to exactly one output? Well, let's start with the input 1. That seems to have exactly one output, and it's 5. The output 2 also has exactly one output. It's 3. But what about the input 3? 3 occurs twice as an input. In the first case, 3 has an output of 4, and in the second case, 3 has an output of 6. So actually, this one input of 3 has two different outputs. Therefore, this is not a function, since the input 3 has two different outputs, both 4 and 6. Now we often use equations to represent relations and functions. For example, let's say we took the equation y equals 2x minus 1. Now, any ordered pair that makes that equation true would be a member of that relation. So we can fill in our table as we normally would. So for example, if the input was 1, then the output would be 2 times 1, which would be 2, minus 1. So it would also be 1. And if the input was 2, and we plug that in for x, we'd get 4 minus 1, so 3. And if the input was 3, we'd have 6 minus 1, so 5. And if the input was 4, we'd have 8 minus 1, so it would be 7. So here is a partial list of inputs and outputs, but actually this relation has an infinite number of inputs and outputs because we could continue this forever if we wanted to. Now the question we want to look at is this a function? Does each input have exactly one output? So the input 1 leads to exactly one output, it's 1. The input 2 leads to exactly one output. The input 3 also leads to exactly one output, and the input 4 also leads to exactly one output. So this is a function because each input has exactly one output. Now the domain of the function would include all the different x's, or all the different inputs that you could put in here. That would include 1, 2, 3, and 4, but it would also include 5, 6, 7, 8, and negative numbers, and decimals, and fractions. So in fact the domain is all real numbers because you can put any number in as an input. And the range of this function is all the different outputs or y values that you'll get. And that's also going to be all real numbers. Next, I'd like to look at the equation y equals plus or minus the square root of x. Now in this case, let's fill in some inputs and outputs. Let's assume x was 1. Well, if x was 1, then we would have y equals plus or minus the square root of 1. Now the square root of 1 is 1, so y would be plus or minus 1. So that means the output could either be positive 1 or it could be negative 1. So if the input is 1, the output could either be 1 or it could be negative 1. So I'll represent that with 2 rows in my table. So the input 1 could either have an output of 1 or it could have an output of negative 1. Now let's try a couple other points. Let's assume that x was 4. So if the input is 4 and we plug that in for x, then y would be equal to the positive or the negative square root of 4, which would be plus or minus 2. So this tells us that the output could either be 2 or negative 2. So if the input is 4, we could have an output of 2, or also with an input of 4, we could have an output of negative 2. Let's try one more. This time let's use an input of 9. In this case, y would equal the positive or the negative square root of 9, or positive or negative 3. So this tells us that the output could either be 3 or it could be negative 3. Now the question now is this a function? Remember, for a function, each input has to have exactly one output. And that's clearly not true here. The input 1 has 2 different outputs. The input 4 also has 2 different outputs. And the input 9 has 2 different outputs. So this would not be a function. Okay, in this example we're given 2 different tables, and in each case we want to decide whether the table represents a function or not. So again, what we're checking for is, does each input lead to exactly one output? So let's look at the table on the left. Looks like the input 4 leads to exactly one output, it's 7. The input 5 leads to exactly one output, 8. The input 6 leads to exactly one output, 8. Now that output happens to be the same as the output for 5, but that's okay. Still, each of these inputs leads to exactly one output. And then the input 7 leads to exactly one output, 9. So this is a function. Now in this second example, the input 1 does lead to exactly one output, 5. The input 2, however, look at it, appears twice as an input. So the same input too has an output of 9 and it has an output of 10. So that right there is going to prevent it from being a function because we have the same input 2 with 2 different outputs, and a function cannot have that. So this is not a function. Now another thing that we'd like to be able to do is be able to look at a graph and right away decide whether or not it represents a function. And the vertical line test makes it very easy to do this. So the vertical line test says that a graph does represent a function if and only if every vertical line crosses the graph at most once. That's the key part there. Every vertical line crosses the graph at most one time. If a vertical line crosses the graph more than once, it's not a function, in other words. So we have 5 different graphs shown here, and we're going to look at them one by one and decide whether or not they represent functions. And so I'll take this vertical line, and what I want to do is kind of slide it back and forth. Will this vertical line ever cross the graph more than one time? The answer is no. The most this vertical line can ever cross the graph is one time, and therefore this is a function. Now let's look at this U-shaped graph, which is called a parabola. Again, I'm going to slide this vertical line back and forth. Will this vertical line ever cross the graph more than once? Again, the answer is no. The most it can cross is one time. So this is a function also. Next, let's look at the graph that's a vertical line. The question is, can this vertical line ever cross the graph more than once? And the answer is yes. If I put it right on top of the line, it actually crosses it an infinite number of times, and that's definitely more than once. So this is not a function. What about this sideways V-shaped graph? Do we think this is a function? Well, clearly if I put the vertical line right here, it does cross the graph in 2 different places. Once right here and once right here. And so this is not a function. And lastly, let's look at the circle. If I put the vertical line over the circle, we see that it crosses the graph twice. Once there and once there. So again, this is not a function. Next, I'd like to talk about how to determine if an equation represents a function. Let's start with the example y squared equals x. We'd like to determine if this represents a function. Now remember, in order to be a function, each input has to lead to exactly one output. And x represents the input and y represents the output. So let's pick an input for x and go ahead and plug it in and see if it leads to exactly one output. Let's pick the number 4 for x. So if the input is 4 and we substitute that into our equation, we get y squared equals 4. Then the question is, what numbers can you square and get 4? And y could either be 2 or y could be negative 2. So we have one input, x equals 4, leading to 2 different outputs, 2 or negative 2. So this is not a function. Now let's try a different example. Let's take the equation y equals 3x plus 2. Again, the question is, does each input lead to exactly one output? Let's try a couple different inputs. Let's say x was 1. Now if we plug that into our equation, then y would be 3 times 1 plus 2, which would be 3 plus 2, which would be 5. So that did lead to exactly one output. So if x is 1, then the output is 5, and that's exactly 1. Let's try a different input. Let's say x was 5. Well, if that's the case, then y would be 3 times 5, which would be 15, plus 2. So that would equal 17. So if the input is 5, then the output came out to be 17, and that's exactly one output. So it seems like every time we put one number in for x, we'll get one answer for y. So therefore, this is a function. Now it's definitely worth pointing out here that this last example was of the form y equals mx plus b. And we know that that represents a straight line. And in fact, anytime we have an equation that's in that form y equals mx plus b, that will come out to be a function. So this type of an equation, y equals mx plus b, is always a function. And we call that a linear function. Next, I'd like to go over something called the rule of 4 for functions, which says that there's 4 different ways of describing or representing a function. 1, by using an equation. 2, by using a graph. 3, by using a table. And 4, by using words. For example, let's take the function represented by the equation y equals 3x plus 2, which is the example we worked with in the last problem. So that would be the equation way of representing the function. Now we can also represent this function with a graph. This is the graph of the equation y equals 3x plus 2 from a graphing calculator screen. We can also represent the same function using a table of x's and y's, or inputs and outputs. So in the left column are the x's, these are all the inputs. In the right column, these are the outputs. And the last way of representing it is by words, and that's to say how the output is related to the input. In this case, the output is 2 more than 3 times the input. It really helps to be able to look at a function from all 4 of these different perspectives. The last topic I'd like to go over in this lesson is showing you how to use a graph to determine the domain and range of a function. Now remember, the domain is the set of all the x values, and the range is the set of all the y values in a function. You can see we have a graph given to us, and we're asked to find the domain and range. Now to find the domain, we want to look at the horizontal variation in the graph from left to right. Remember, we're dealing with x values when we talk about domain. So if we're working on the domain, we want to be looking from left to right. The question is, how far to the left does the graph ever go? What's the farthest to the left it ever gets is right here. And the x-coordinate there is -2. So that will be the smallest the x-coordinate will ever be. And what's the farthest to the right the graph ever goes is right here, and the x-coordinate there is a 3. Therefore, the domain will consist of all numbers between -2 and 3, which we'll write down in the following way. Put the smallest number down first, -2, and then less than or equal to x in the middle, and that's less than or equal to 3. That's the easiest way of writing down that x has to be between -2 and 3. Now for the range, we're looking at the vertical variation in the graph. How low does the graph get and how high does it get? And we're measuring it by y values now. So the lowest the graph ever gets is right here, and that's at a y value of -2. And the highest it ever gets is right here at a y value of 4. So when you write that down, you always want to write the smallest number down first. So -2 is the smallest the y value ever gets. It's less than or equal to y. and then put the biggest value on the right side, which would be 4. Okay, let's try another example. First we'll try to find the domain. So we're thinking from left to right in terms of x-coordinates. How far to the left does the graph ever go? Looks like right here at an x-coordinate of -3. And how far to the right does the graph go? Right here to an x-coordinate of 3. So the domain would say that the x-coordinate is always between -3 and +3. And for the range, we want to think in terms of how far down does the graph ever get. Now the farthest down it ever gets is right here or right here. It's actually equally low at those 2 points, which has a y-coordinate of 0. And the highest the graph ever gets is right here, and that looks like a y-coordinate of 3. So the y-coordinates are always somewhere between 0 at a minimum and 3 at a maximum. So we'd put the smaller number first. 0 is less than or equal to y is less than or equal to 3, meaning y is always between 0 and 3. Let's just try one more of these. Here we have a new graph, and we're going to find the domain first. So we want to ask ourselves, how far to the left does the graph go? Now in this case there's no end there, it just keeps going according to that arrow. It's going to go forever. Okay, so there's no end to how low the x value is going to get, because that's going to keep going off to the left, slowly but steadily. And on the right side, you can see that that's also going to veer off to the right. So the x-coordinate is going to get bigger and bigger on the right side with no limit either. So in this case, the domain is all real numbers. In that case, you should just write that out. Now let's look at the range. We want to see how far down or low does the graph get. The lowest points appear to be at these two, and the y-coordinate there is at 1. So that's as low as it ever gets. And how high does it get? Well, it goes up forever, so there's no limit to how high it can get. But the y-coordinate is always greater than or equal to 1. So that would be the range. That y is always greater than or equal to 1.